operates lightning fast and, in perfect sync.
Absolutely. And we've got some great material to work with today. Insights pulled from a really detailed book all about static timing analysis.
Okay.
It covers, well, pretty much everything from the ground-up CMOS basics right through to the really complex stuff like crosstalk and how variations across the chip mess with timing.
Our mission, like always, is to take all this information and pull out the most critical stuff for you. We want to make even the trickiest STA concepts really clear.
And maybe find a few surprises along the way.
Hopefully. So whether you're already deep in chip design or just curious about how your tech ticks, you're definitely in the right place. Okay, let's dive in.
Let's do it.
First up, maybe a quick refresher on the absolute foundation CMOS logic. As we know, it really boils down to NMOS and PMOS transistors.
Yep, those tiny little switches, they're the fundamental building blocks.
And if you hook them up cleverly, like in a CMOS inverter, you start building more complex gates, like NAND gates, right?
Exactly. And from those basic gates, we get what are called standard cells. Think of them like pre-designed, pre-tested Lego bricks.
Okay.
They have well-defined functions, well-defined timing. You basically snap them together to build your bigger circuit.
Gotcha.
And here's something really key. Power in CMOS circuits, it's mostly used when those transistors are switching on, off. Not so much when they're just sitting there stable.
That's a really important point, especially now with everyone pushing for low-power devices.
Absolutely. It's critical for understanding power consumption.
Okay, now let's get into some essential timing terms. First one, propagation delay. What's the core idea there?
Simply put, it's the time it takes for a change at the input of a gate, a logic gate, to actually show up at the output.
So how long it takes to react?
Pretty much. It's the react time metric. And it's critical because if signals get delayed too much, well, they might miss the window for the next operation. The whole circuit could just fail.
Makes sense. Okay, next is slew, or transition time. This sounds a bit more involved.
It is, a little. Slew describes how quickly a signal changes voltage, the rate of rise or the rate of fall.
Okay.
Our sources mentioned it's often measured between specific voltage points, like 20% to 80%, or maybe 10% to 90% of the supply voltage.
Right.
Interestingly, for modern chips, they often use 30% to 70% now. It gives a better picture of the more linear part of the signal change.
Why is slew so important then?
Well, slow slews don't just add to the propagation delay we just talked about. They also waste more dynamic power. That's a huge deal in low-power design.
Got it. So a sluggish signal hurts speed and power. Okay. What about skew? I hear that term quite a bit.
Skew is the difference in arrival times of same signal, but at different places in the circuit.
Okay.
Imagine, like a clock signal, trying to hit two different flip-flops at the exact same time. But because the wires take different paths, it arrives slightly later at one. That difference, that's skew.
And it causes problems.
Oh, yeah. Big headaches, potentially. One part of your circuit might be using old data, while another part has already moved on because the clock arrived at different times.
Okay, definitely something you want to minimize. The outline also mentions timing arcs and unnateness. This sounds like we're getting into the real nitty-gritty of how signals move through cells.
Exactly right. A timing arc just represents the delay path from an input pin to an output pin of a logic element. And unnateness describes the relationship. Is it positive unnateness, meaning the output changes in the same direction as the input? Like NAD gate input goes high, output potentially goes high.
Okay.
Or is it negative unnated, meaning the output goes in the opposite direction? The classic example is an inverter. Input rises, output always falls. That consistent opposite reaction. That's negative unnateness.
So the STA tools use this unnateness info to understand how a change propagates.
Precisely. They know if the signal will flip or stay the same, and roughly how long it should take.
Interesting. So for an OR gate, if any input goes high, the output goes high. That'd be positive undelete too.
Exactly. The output follows the input's direction towards high.
Right. And then we have min and max timing paths. These sound absolutely crucial for figuring out the speed limits of the circuit.
They are totally vital. Look, in any digital circuit, signals can take loads of different routes. The max path, that's the one with the absolute longest total delay.
And that sets the maximum clock speed.
You got it.
Okay.
It dictates how fast you can reliably run the whole thing. The min path is the opposite, the shortest delay path. And that's critical for avoiding something called hold time violations. Probably get to those later.
Okay.
And path delay itself, that's just the sum of all the delays along one specific path, the cell delays plus the interconnect delays.
Got it. Slowest path sets the speed limit. Fastest path can cause other problems. Makes sense. Finally, in this first section, Operating conditions, PVT. It's not enough to just analyze in a perfect world, is it?
Not even close. The real world is messy. Transistor performance, wire behavior, it all changes massively depending on manufacturing variations, process, the power supply voltage, and the chip's temperature. PVT.
Right.
Chip makers actually give you different models for the process variations: slow, typical, fast. These represent the natural spread you get during manufacturing.
So cell delays change depending on whether you got a fast chip or a slow chip off the line.
Exactly. And they also change with voltage fluctuations and temperature swings. So these aren't just theoretical corners, they represent the real manufacturing tolerances and operating conditions your chip has to survive.
So you have to test your design under these different, sometimes extreme conditions.
You absolutely do. Our materials talk about worst-case slow, WCS conditions. That's where manufacturing gives you slower transistors, the temperature is high, which also slows things down, and the voltage is low. It all adds up to the longest possible delays.
The absolute slowest it could possibly run.
Right. And then there's also typical leakage, TL. Process and voltage are typical there, but the temperature is high. This reflects how hot the chip might actually get in operation and how that affects power leakage.
Okay, that gives us a good foundation. Moving into section 2, we're looking at how these library cells, the building blocks, are actually described for the timing tools. The book says standard cell libraries hold all the timing and power info.
They do. And a really common way to model delay in these libraries is the nonlinear delay model, or NLDM.
Nonlinear. Why nonlinear?
Well, the delay through a cell isn't just one fixed number. It actually changes. It depends on how fast the input signal is changing. That's the input slew or transition time, and how much stuff the output has to drive the output load capacitance.
Yeah.
And LDM captures this complex relationship using basically two-dimensional lookup tables.
So like a grid. Input speed on one side, output load on the other, and the delay is in the middle where they meet.
Exactly. And the library usually has similar tables that also tell you how fast the output signal will transition its slew for that same input slew and output load.
So you look up both the delay and the output slew.
Yep. And the tools are smart. If the exact input slew and load aren't in the table, they use interpolation, basically making a very educated guess based on the surrounding table values.
That sounds pretty sophisticated. Making predictions based on the data. Now, the outline mentions threshold specifications and slew derating. We talked about slew thresholds. How does derating fit in?
Right. So, as we said, older libraries might have measured slew between 10% and 90% of the voltage swing. Newer ones often use 30% to 70% because it's, well, arguably more accurate for modern tech.
Okay.
To bridge that gap, they use a slew derate factor. It's a multiplier. For instance, a derate of 0.5 might mean you multiply the 30-70% slew by 2 to get an estimate of the 10-90% slew.
Conversion factor.
Pretty much. It helps keep things consistent when you're mixing libraries or tools.
Clever. Okay, next. Timing models for combinational cells. We touched on unaidness. How's that actually represented in the library for a cell?
So for every possible pass from an input to an output in a combinational cell, the library defines a timing arc. That arc contains the delay info, usually from those NLDM tables we just discussed, and it specifies the unaidness, positive or negative.
So NAND gate, input goes high, output goes low. That's opposite.
Right. So a NAND gate would have negative unaided timing arcs from its inputs to its output. An AD gate, on the other hand, where the output follows the input going high, would have positive uninnate arcs.
Okay, so the library meticulously defines how signals propagate through every single standard cell. What about sequential cells? Flip-flops, latches, they have clocks, which must add complexity.
Oh, absolutely. Huge complexity. For sequential cells, like your basic flip-flop, you still have propagation delay arcs, specifically from the clock pin, usually CK, to the output pins, Q and maybe QN. These delays tell you how quickly the output changes after the clock edge hits. But that's just the start. Sequential cells have critical timing checks that must be met for them to work right.
Timing checks? Like what, specifically?
The big ones are setup and hold checks. Setup time is the minimum time the data signal has to be stable before the active clock edge arrives.
So the data has to be ready early.
Exactly.
Yeah.
And hold time is the minimum time the data has to stay stable after the active clock age. If it changes too soon, the flip-flop might grab the wrong value.
Okay.
And these requirements, setup and hold, are often given in those 2D tables again. They can depend on how fast the data is changing and how fast the clock is changing. The faster things transition, the tighter these windows might become.
Wow, so it's a real delicate dance between data timing and clock timing.
It really is.
Yeah.
And there's more. The library also includes recovery and removal checks for asynchronous signals, like a reset pin.
Asynchronous meaning not tied to the clock.
Right. Recovery time is how long the reset needs to be inactive before the clock edge. Removal time is how long it needs to stay inactive after the clock edge.
More timing windows to worry about?
Yep. And finally, pulse width checks. These make sure the clock pulse itself and any asynchronous signals are wide enough, or sometimes not too wide, to guarantee the flip-flop works correctly.
Lots going on in just one flip-flop.
Seriously. It's amazing how much timing detail is packed in there. Now, the outline mentions state-dependent models. When would a cell's timing depend on the logic state of its other inputs?
This is where it gets even more subtle. Sometimes a cell's timing isn't fixed. It changes based on what's happening at its other inputs. The example our materials use is an XOR gate.
Okay.
The timing path from input A to the output might be positive on the 8 if input B is low. But if input B goes high, that same path from A to the output might become negative on 8. The gate's effective behavior, timing-wise, changes based on the state of its other inputs.
That makes sense. And XOR's output depends on both inputs changing its function. Exactly. And state-dependent models are also really common for those setup and hold constraints in sequential cells. Think about a scan flip-flop used for testing.
Right.
The setup and hold times might be different when its scan enable pin is active versus when it's inactive during normal operation. The library can hold both models, and the tool picks the right one based on the state.
And this state dependency can even affect power.
It can, yeah.
Yeah.
Leakage power especially can change quite a bit depending on the internal state of the logic.
That's incredibly detailed modeling. What if we have a whole chunk of logic, but we don't know the internals, a black box? How do we model its timing?
Good question. For those cases, we use an interface timing model. It essentially describes the timing just at the inputs and outputs of that black box.
So it uses the same kinds of timing arcs we've been talking about.
Exactly. Combinational arcs, sequential arcs, setup-hold checks on inputs, clock-to-output delays, and yes, these can also be state-dependent. You can also define pulse width checks on any external clock pins for the black box.
So it's like a timing data sheet for this mystery block.
Precisely. It lets you analyze the system without needing every last detail of the block's internals.
Very useful. Okay, the final part of this section gets into advanced timing modeling. Sounds like the cutting edge for library characterization.
Yeah, this is where things get even more sophisticated to handle modern effects. For instance, our materials mention that receiver capacitance, the capacitance seen looking into an input pin, might actually be different for a rising signal versus a falling signal.
Really? Huh.
Yep. So the library might specify different capacitance values. Then there's the output current, CCS model. Instead of just simple delay tables, this model characterizes the actual output current waveform of the cell.
Output current over time.
Right. It depends on the input transition and the output load. It gives a much more accurate picture of the cell's driving strength, especially under complex loading conditions.
That sounds very electrical engineering focused.
It is. And rated are CCSN models. N for noise. These are often used for specific connection points in complex cells and can include info about steady-state current, output voltage, and noise characteristics.
Noise models, too.
Yep, CCS noise models. Can be tied to a pin or a specific timing arc.
Yeah.
And finally, for robustness, libraries can specify noise immunity margins, basically defining the voltage thresholds for valid logic levels and how much wiggle room you have against glitches, like overshoot and undershoot.
Wow, trying to capture every little real-world effect. And this section finishes with power dissipation modeling. Makes sense, given how critical power is.
Absolutely. Libraries contain info on both active power, used during switching, and standby power, leakage when idle.
Mm-hmm.
These are often in tables, too, depending on input transition and output load, telling you the energy per switch. The library also specifies power ground pins, maybe power down modes, and even state-dependent power.
And for flip-flops.
They're careful to account for the power used by the internal clock bits separately from the output switching so you don't double count. And crucially, the materials note that leakage power, especially subthreshold leakage, is super sensitive to temperature. Higher temps mean more leakage.
Okay, that's a lot packed into those libraries. Section 3 shifts focus now from the cells themselves to how they're connected. Interconnect parasitics and delay calculation. This is where the physical layout starts to really matter.
Oh, absolutely. Huge impact. In these nanometer technologies, The resistance and capacitance, C, of the actual metal wires connecting the cells, they often dominate the overall timing.
Not just the cells themselves.
Not anymore, no.
Yeah.
The wires are a huge factor. Our materials stress how the specific metal layer a wire is on, its length, its width, all that directly impacts its R and C values.
So a long, skinny wire up high is different electrically from a short, fat wire down low.
Exactly.
Yeah.
Now, before you even have the final layout, you need some way to estimate these effects. That's where wire load models come in. They're statistical models. They predict the R and C based on things like how many pins the wire connects to the fan out, or maybe just an estimated wire length. You can even use different models for different parts of your design.
So wire load models are the pre-layout guess. What happens after the chip is laid out physically?
After layout, you do what's called parasitic extraction. Tools analyze the geometry of materials and figure out the actual R and C values for all the interconnects.
And how is that data stored?
Our materials mention a few formats like DSPF and RSPF, but the main one used today is SPF, Standard Parasitic Extraction Format.
SBF. Okay.
It's compact, comprehensive, includes resistance, capacitance to ground, and critically, coupling capacitance between adjacent wires. That's the key ingredient for crosstalk, which we'll get to.
Coupling capacitance, the electrical link causing interference.
Got it. The book also mentions a hierarchical methodology for parasitic extraction. How's that work?
For really big chips, extracting everything at once is, well, computationally brutal. So often you extract parasitics for individual blocks or modules first. Right.
Then, at the higher level, you use these extracted parasitics for the completed blocks. For parts not yet finished, you might still use those wire load models. It lets you analyze timing progressively.
Makes sense. Break the problem down. Now, how do we actually calculate the delays pre- and post-layout?
Okay, pre-layout timing uses those estimated wire load models for interconnect delay, plus the cell delays from the library using an LDM. Post-layout timing uses the detailed RC networks extracted from the layout, the SFB file. Cell delays are still calculated using NLDM, but now the load includes the actual resistance and capacitance of the wire attached.
And the delay of the wire itself, the interconnect in post-layout, how's that calculated?
Using RC delay models, a common one mentioned is Elmore delay. It's an approximation, but often pretty good for estimating delay through an RC network.
Okay.
Our materials also mention using a 7-in source model. That's a way to simplify the driving cell down to an equivalent voltage source and series resistance when you're calculating the delay through the interconnect it's driving.
Like simplifying the driver's characteristics and putting it all together for a signal crossing the whole chip.
Full chip delay calculation involves tracing signals step by step. The output transition time, the slew, from one cell becomes the input slew for the next cell it drives. You propagate these transitions and delays through every cell and wire segment.
Sounds like a massive calculation. The outline also mentions slew merging. What if multiple signals arrive at the same spot with different slews?
Good point. When paths converge, say at a gate input, you might have different slews arriving. For max path analysis looking for the longest delay, you typically propagate the worst, meaning the slowest, slew forward. Slower input usually means longer delay through the next gate.
And for min-path?
For min-path analysis, looking for the shortest delay, you'd usually propagate the best, the fastest slew. Though more advanced methods exist that consider arrival times too.
And we still need to remember that slew derating factor we talked about, potentially converting between measurement thresholds.
Absolutely. That can still apply here, depending on library specs and tool settings.
So, finally, the total delay of a whole path.
Path delay calculation is fundamentally just summing it all up. Add the delay of each cell along the path, and the delay of each interconnect segment connecting them. The materials show a simple example with inverters in series. Just add up the stage delays for the total path delay.
Got it. Okay, Section 4 gets into something critical for modern chips, crosstalk and noise analysis. As things get smaller and denser, this unwanted interference gets worse, right?
Absolutely. Yeah. The materials really stress this. Noise, any unwanted electrical signal, can seriously mess with both functionality and timing in these nanometer designs.
Why is it getting worse?
More metal layers packed closer together, smaller wires, smaller transistors, it all contributes.
So what are the main noise sources we worry about?
Well, one basic concept is DC noise margin. That's basically the voltage buffer zone a gate has. If noise stays within the Vilmax and VIH min limits, the gate should still interpret the signal correctly.
Like a built-in filter?
Sort of, yeah. But the big one for timing is crosstalk.
That's signals on nearby wires interfering.
Exactly. It's mainly caused by that coupling capacitance between wires running close together. When one wire, the aggressor, switches voltage quickly, it can induce a voltage glitch on a nearby wire, the victim, through that capacitance, like electrical shouting between neighbors.
And how does that glitch affect the victim signal's timing?
It can do two things, actually. Positive crosstalk happens when the aggressor switches in the opposite direction to the victim. This makes it harder for the victim's driver, effectively slowing the victim signal down, increasing its delay.
Okay, slower makes sense.
But there's also negative crosstalk. That's when the aggressor switches in the same direction as the victim. The coupling capacitance can actually help the victim switch faster, decreasing its delay.
Whoa, so crosstalk can speed things up too? That seems counterintuitive.
It does, but yeah. And that speed up can be just as bad as a slowdown if it causes a hold time violation.
Right, data changing too soon.
Exactly. So crosstalk delay analysis has to look at both possibilities, increased delay and decreased delay. And it gets complex because one victim wire might have multiple aggressor wires nearby.
Oh boy.
The analysis needs to figure out which combination of aggressors switching at roughly the same time causes the biggest impact, positive or negative, on the victim's timing. It looks at overlapping timing windows.
That sounds incredibly complicated to analyze. So many potential interactions. Is there any way to simplify it?
Sometimes. There's a technique called aggressor-victim functional correlation. The idea is some signals only switch during specific modes, like scan signals for testing might be quiet during normal operation.
Ah, so you don't need to worry about them being aggressors in functional mode.
Precisely. If you know certain signals won't be switching simultaneously with the victim in the mode you're analyzing, you can tell the tool to ignore them as potential aggressors. It prunes the analysis significantly.
Okay, that helps manage the complexity somewhat. Section 5 now shifts to how we actually tell the STA tools what to do. Using Synopsys Design Constraints, SDC, this is like the instruction manual for the analysis.
That's a great way to put it. SDC is the rulebook. And the absolute first, most crucial rule is clock definition. You use the create clock command.
And what do you specify there?
The clock's period, its waveform rise time, fall time, and the specific port or pin in your design where this clock signal originates.
So you can define more than just a simple 50% duty cycle square wave?
Oh yeah. The do waveform option lets you define exact rise-fall times, different duty cycles, whatever the clock actually looks like.
Okay.
And the materials distinguish between ideal clocks assume to have zero delay getting into the chip and propagated clocks, where the tool actually calculates the delay through the clock distribution network. You can also specify the clock's transition time, slew, right at the source.
What about the delay after the clock source pin getting to all the flip-flops?
That's clock latency. There's source latency, which is the delay from the off-chip source to your clock definition point.
Yeah.
And then network latency, which is the delay from that definition point through the on-chip clock tree to the actual flip-flop clock pins.
Got it. And what if you have clocks inside the chip that are derived from others, like a divide by 2 clock?
Those are generated clocks. You use the create generated clock command. You tell it which master clock it comes from, how it's derived, like division, and which edges relate to which. You could even add shifts for phase control.
So SDC lets you map out the whole clocking system precisely. What about signals coming in from outside or going out? How do you constrain those?
That's input and output constraints. Set-input delay tells the tool when external signals arrive at input ports relative to an internal clock edge. And set-input delay tells it when signals need to leave the output ports, again, relative to a clock edge, to meet external requirements.
And these delays have ranges, like earliest and latest arrival.
Yes, exactly. You specify min and max delays for both input arrival and output required times, and you also need to model the outside world electrically.
How so?
Using commands like set drive or set driving cell to model how strong the external driver is. Set load specifies the capacitance the output pin sees externally, and setmem transition tells the tool the expected slew rate of incoming signals.
Okay. Now, sometimes certain paths in a design aren't real paths functionally, or they take multiple cycles. How do you handle those exceptions?
Right, path exceptions.
Yeah.
Set false path tells the tool, ignore this path completely. It's never functionally active.
Okay.
Set multi-cycle path says, this path needs more than one clock cycle, so adjust the timing check accordingly.
Right.
And set disable timing lets you remove specific timing arcs inside a cell. But the materials warn you need to be really careful with that one. Easy to hide real problems if you misuse it.
So understanding the design's function is key to setting these exceptions correctly. Can you constrain delay between any 2 points, not just clock paths?
Yeah, point-to-point delay constraints. Set max delay and set min delay. You can put timing limits between any two arbitrary pins in the design.
Useful for specific interfaces, maybe.
Exactly. And lastly, the materials mention path segmentation. You can use input-output delay commands kind of creatively to define intermediate start endpoints on a long path, letting you analyze segments individually.
Okay, that gives us the rules. Section 6 brings us to the actual timing verification and advanced topics. This is where we see if the design passes or fails.
Exactly. And the fundamental checks are setup and hold. For setup, the tool compares the data arrival time at a flip-flop's input with the data required time.
Required time being based on the clock edge plus the flip-flop setup requirement.
Precisely. The difference is the slack. Positive slack, good, you have margin. Negative slack, bad setup violation. Data arrived too late. Tools can even plot histograms of slack across all paths.
Gives you a feel for the overall timing health. And hold checks. That's about data not changing too soon after the clock.
Correct. Hold compares the data arrival time, when the earliest possible change could arrive, with the required time used on the capture clock edge plus the hold time requirement. Negative slack means a hold violation. The data changed too quickly after the clock edge.
And those can be nasty to debug.
Oh yeah, can cause really intermittent, weird failures.
We also mentioned multi-cycle paths. How does setup hold work there?
Well, for a 2-cycle path setup check, the capture clock edge is 2 cycles later than the launch edge. For hold, you usually need specific constraints to make sure the data stays stable relative to the first clock edge, preventing it from changing too soon for the later capture.
Okay. What about designs with different clock speeds or phases interacting? Clock domain crossing, CDC?
CDC is a huge deal. Our materials mention fast to slow and slow to fast transfers. You typically need special synchronizer circuits like 2 or 3 flip-flops in a row to handle these safely.
And STA's role?
Standard STA can check the timing within each clock domain leading up to the crossing, but it doesn't typically analyze the metastability risk at the crossing itself. That needs specialized CDC analysis tools or very careful design and constraints.
So extra caution and specific techniques needed for CDC. What about designs with just multiple unrelated clocks?
If clocks are truly unrelated, STA usually analyzes paths within each domain separately. Paths between unrelated domains are often declared as false paths unless there's a specific constrained asynchronous communication protocol.
Okay. And analyzing the chip's boundaries. Interface analysis.
Yep, applying those input-output delay constraints. The materials show examples like constraining inputs based on datasheet AC specs and constraining outputs relative to internal clocks, maybe even multi-cycle outputs. It also mentions source synchronous interfaces like DDR memory, where timing is relative to a data strobe DQS signal.
Right. Now, chips aren't perfect. Things vary. On-chip variation, OCV, how does STA handle process, voltage, temperature variations across the chip itself?
OCV tries to model that. One concept mentioned is common path pessimism, CPP removal. If the launch and capture clock paths share a segment, applying worst-case slow delay to both is too pessimistic, because that shared part will vary the same way. CPP removal corrects for that.
Avoids double counting the pessimism.
Exactly. We also use timing derating. This means applying factors to make paths artificially slower or faster in the analysis to account for expected variations. You might slow down late paths for setup checks and speed up early paths for hold checks, adding safety margin.
Building in margin for real-world imperfections. The book also mentions robust verification beyond standard setup hold.
Right. Things like data-to-data checks, ensuring timing between 2 non-clock signals. Non-sequential checks can be defined in libraries for specific timing rules between data pins. And very important, clock gating checks.
Checking the logic that turns clocks on and off.
Exactly. Need to make sure the enable-disable signals for clock gates meet setup and hold relative to the clock they are gating to avoid glitches. Critical for low-power design.
And with chips having different power modes, how does power management affect STA?
Hugely. Different modes mean different voltages, maybe different parts of the chip shut down. This drastically changes delays. So you need multi-corner MMMC analysis. Run STA across all relevant operating modes, all PVT corners, maybe different interconnect corners too, all in combination. Ensure timing works everywhere.
Sounds like a lot of analysis runs.
It is. Finally, the materials mention statistical static timing analysis, SSTA. How's that different from the deterministic STA we've mostly discussed? Deterministic STA uses fixed values for a given corner, for example, worst case slow. SSTA says, hey, these parameters aren't fixed, they vary statistically.
Okay.
It uses statistical models for process variations, global and local, and interconnect variations. Libraries provide timing models with mean and standard deviation.
So the result isn't just pass-fail.
Right. SSTA gives you a probability distribution for the slack. You can see the mean slack, the standard deviation, and determine the likelihood of meeting timing based on statistical confidence. It's a more nuanced view of timing reliability.
Interesting. And the section ends with the debugging example, incorrect load spec causing huge buffer delays, a reminder that the inputs to STA matter.
Absolutely. Garbage in, garbage out applies just as much here.
Wow. Okay. We have really covered a massive amount of ground on static timing analysis. It's so clear that getting timing right is, well, incredibly complex, but absolutely essential for modern electronics.
It really is. As we've seen, it touches everything from the basic physics of transistors to how cells are modeled, how wires behave, how the environment varies. It's all interconnected.
And that close link between timing, power, and just plain reliability comes through really strongly.
Definitely. And it's fascinating how the methods, the STA tools themselves, are constantly evolving to handle smaller technologies, more complex designs, new effects like crosstalk and variation.
Absolutely. As designs get more and more intricate, like you said, STA isn't just a final check. It's fundamental to the whole design process if you want something functional and high performance.
Couldn't agree more. Which maybe leads to a final thought for you, the listener. As this complexity keeps climbing, what other aspects of design verification do you think will become more and more critical in the future?